Hey, what's up, guys? Yeah, so this is my second video about stochastic calculus, and so I will first talk about rules. I will spend like the 3 or 4 videos talk about rules and basic, and after that, hopefully in the future they will understand. I will try to understand the proof. Okay, so today I just talk about Ito formula or Ito's formula. And then basically one can use this idea to solve the stochastic differential equation. So in this video, I only tell about rule. Okay, so the proof that I will give in the future, hopefully. Okay, so yeah, so this will just be a rule. So let's just give you the informal derivation. So I think the stochastic differential equation that my understanding is that it's like the usual PDE, right, or the ODE that you can write. So basically for ODE that you can write the differential as a function of original or you can write your differential to be something, right? Let's say f of y and x, right? But for stochastic differential equation, that what you're solving is the so-called stochastic process. So we are solving some continuous random variable, although definition of continuous random variable may be tricky. So this is why I mean rigorously you really need to define a like major space, right? You need to use the major theory to write everything clearly. But like informal way that I can just let's say I have a dxt process, right? Suppose our dxt some function mu dt plus let's say sigma dwt. So this is you can view this is like the standard like PDE, right? So in PDE that you can write some variable x, right? Sorry, maybe some f to be as some dx plus some dy, right? Usually this kind of thing is like just a total differential. But in this case, since we are talking about a stochastic one, right? So we should write the stochastic process as dt and the Brownian motion. Okay, so it's 2 parts. So you can view this is the standard differential part, and this is the weird part. This is basically there's a stochastic part that you can, for each step that you can add one very small Brownian motion. Okay, so what Ito's formula tell you basically tell you the following. Basically, if someone you start from f, t, and x, and then you want to compute the df. Okay, so this is the results. This is what we're gonna do is that we just try to compute df. Okay, so you can just prove this or informal prove this, or you just remember the answer. Okay, so let me just remember the answer. So you can do df. So the easy way to derive is that by the way, this is not derivation, this is just a rule that I tell you. So df is basically you see your idea of chain rule, right? You get partial dt, partial d f dt plus partial x f dx, right? This is the chain rule. But in this case, you need to add a second term. So this second term, I only add about x term. Okay. Okay, and don't ask me why. This is just informal definition. So informal derivation. So if you want to know more, maybe in the future. Okay, and you also know that your dx is mu dt plus sigma dwt. So in this, notice that in this notation that the mu and sigma are basically can be function of t. Okay, can be function of t. So some people will write this, but I think this notation is so confusing, so I will not do this. Okay, so partial d dt plus partial x f. Okay, so this is you can view this is rule number 1. So dx squared. Okay, and dx, so I just mu t dt plus sigma t dwt plus half of second differential. So second differential goes as this. Now dx squared. So rule is this, right? For dx squared, that every term will disappear unless dwt squared. Okay, so dwt squared you need to replace to be dt, and the reason is that you have your wt is basically the normal distribution of 0t, and so you can view this dw squared should be the variance of wt, right? So if you calculate the variance of this guy become t, so you can imagine that it's become dt. And there's a rigorous proof for this, but let's skip. Okay. So the rule number 1 is this. Rule number 2 tell you that dx squared must replace by sigma t squared dt. or basically one can say that the Brownian motion is or this Brownian dwt is basically the square root of dt. Okay, so right, so one easy way is that you imagine that this is this. Actually, when you do the Python calculation, you really do this. Okay, so it becomes dt sigma square. Okay, so combine everything, you get partial df, mu partial f partial x plus half of sigma square, partial square partial f partial x square, and plus sigma t partial x f dwt. Okay, so yeah, so this is the results. So basically df is this. Okay, and this is basically Ito formula. So you need to remember it. Okay, and this derivation is actually obviously not rigorous, but it's fine. Okay, we are not doing an analytic number theory, so we are good. Like we don't need to like prove something very difficult. Okay, and okay, so we need to like yeah, so let's win this. Okay, hopefully we can. I guess that can I copy this equation? Probably no. Okay. Okay, fine. Okay, so now okay, so in order to keep going, let me just solving one right. So this is like textbook example, but it's very enlightening that you can use this stupid formula or weird formula to do this. Basically called the geometric Brownian motion. Okay, so the idea is the following, right? So somebody give you a DST called the sigma st dwt, let's say plus mu of mu st dt. So you can view this is mu st dt plus sigma st dwt. Okay, so this is like this is the equation. Okay, and usually you don't care about this. Some people will just I would really like to write ds just equals to mu s mu I would like to write ds. I would neglect this t symbol, so I would just write ds equals to mu s dt plus sigma s dw. Okay, this looks like the standard differential, right? So our goal is to solve what? To solve s. Okay, so obviously that you know answer, right? If sigma is 0, you know that it's just ds equals to mu s dt. Okay, in this case, everyone need to solve, right? This is the separated ODE, right? So you just write this and do the integrals, right? You just get log s equals to mu t plus constant. So you know s is exponential mu t plus something. Okay, but in this case, that since geometric, so we add some Brownian motion term. So we need to like solve the results. And then basically your s is not a function, it's the testing process. So your s of t will be basically your final results s of t will be not just a function, right? There will be some parts that related to Brownian motion. Okay, so will be not just okay, so it's not just function of t, right? Will be function of t and then some Brownian motion. Okay, and so enlightening by this, that we can consider this, right? So we can consider function. We can consider a function like log s. Okay, so now let's play. So it's simple, right? Just play a rule. So we know that ds is basically mu s dt plus sigma s dw, and we know, let's say f is 1 over like log s. Okay, now we use a Ito formula. I think it's very important that you solve sigma equals 0, so that give you high hint that f equals to log s is a good choice for f. Okay, so let's yeah, let me just quickly write down. So if you go back to see my video that you know this df, let me just write down formula. I think it's partial df plus partial x f and mu, but this is called mu t. So in this case, it will be mu s plus the second derivative, sigma t squared dt plus plus what? Plus the term, right? So plus the term by dw and partial f partial x, so it's sigma t partial f partial x. Okay, yeah, just partial x f. This is equation true for ds or dx or dx equals to mu t dt plus sigma t dw. Okay, so this is Ito's formula. Let me just copy this. Okay, so let's do this. Okay, so in this case, right, obviously that I should what? I should just replace our x to be s. Or I should replace my x to be s, right? So I just this is x I just change to s, and now I do this f to be log s. Okay, so let's do this. So about df, right? So this is just s of ds, right? This is chain rule, right? Okay, so partial d f, maybe this is not a good way. Let's do this. So f is log s. Okay, now what's partial tf is 0. Okay, partial sf is 1 over s, and then we need to do the second derivative, right? So we have partial ssf. Now x is replaced. X is the x and s are the same. Okay, so just this. Okay, and that's it. So we have this. A partial xf will give me 1 over s, right? Now mu, right? Mu t is basically mu s, right? So mu s, oh, s different, right? Cancel. Good. Plus sigma t. Okay, so plus half of, right? Now you know this definition. Now you know this is like well-ly designed, right? So sigma t in this case is sigma s squared. So in this case, let me just write down. So mu t is mu s, sigma s is sigma t. So in this case, that the mu t are basically the function of mu and s. Mu sigma t is basically sigma of s times s. So mu and sigma are constant. So these are special forms, right? In general, if you put these two, then probably it's very hard to solve. dt plus sigma t with sigma s times 1 over s dwt. Okay, so your dss will be just mu minus sigma squared divided by 2 dt plus sigma dwt. Okay, so notice that this is trivial, right? This equation trivial looks like exactly the same as this. Okay, so you just integral by part. Sorry, you integral both sides. Okay, so you got log s, right, equals to log of s0 plus integral of this, right? But this is like two special component. Sorry, two special variable, two separated variables. So you just integrate by itself. So just t plus sigma wt. Okay, this is trivial because dt, integral of dt is t, integral of dwt is wt. Okay, so this is the result. Okay, so we can just write out our final results as s0 exponential of exponential what? The mu minus sigma squared divided by 2 t plus sigma wt. And it's true, right? If you put sigma to be 0, then you get our very simple results. Okay, so this is the results. Okay, so the first very simple calculation of this geometric Brownian motion. I think this is the same as the Black-Scholes model, Black-Scholes formula. Yeah, I think this is also the same as if you this model also applicable in this Black-Scholes. I think for Black-Scholes, sorry, how to pronounce it. Okay, forgive me, I'm not like Black-Scholes model. So for Black-Scholes model, I think it's also used the same proof. Okay. Yeah, exactly. Probably, I guess exactly the same proof. Okay. Okay. Yeah, so this is the first implication of geometric motion, that geometric Brownian motion that we derive the results. And in the next 2 or 3 videos that I keep doing like more results. So so we will like have many chances to play around with this weird formula. See you guys.